Hello, class. This is Mr. Hart. Sorry I can't be there today. I had a praxis test that I had to go take, but I'm making this podcast so they can still cover material. I know we were working on the bridge building project, but we will have some time next time to finish that up before we crush the bridges. Okay, so on Monday you can do the last steps you need to make sure your bridge is complete. Okay, and then we'll crush them on Wednesday. But I wanted to go ahead and move on to the next unit so we can finish it up before Christmas break. And the next unit is momentum. Okay, and we want to be able to describe momentum. It's very similar to force in a lot of aspects, but we deal with it slightly differently. Okay, and so we want to be able to know how to calculate it, what it is, what it means, and all that type of thing. Okay, so first of all, let's just talk about what is momentum. What does it mean? Why is it important? What is it used to? Or what do we use it for, I mean. Okay. So you probably have heard it a lot in terms of like sports, for example. If you've ever played football, you may have heard someone say, oh, that guy's got a lot of momentum. Or when someone gets tackled, you can see the momentum. Okay, there's a lot of phrases we use to describe momentum. Okay, you probably have an intuitive idea of what momentum is, but we want to make sure we describe it clearly, assign mathematical terms to it and that type of thing. Okay, and so when we're talking about momentum, we are strictly talking about a quantity, a physical quantity that we can measure and calculate, okay? And this is how we measure it and how we determine it, okay? So momentum is the ability of an object to continue moving in a given direction, okay? And it is described by this equation down here, okay? And so the letter P, lowercase p, is the letter we use for momentum, okay? Don't ask me why that is. I'm not really sure, to be quite honest. Okay, but momentum is described with lowercase p. Okay, that's momentum. Okay, and then it is equal to the mass times the velocity. Okay, so mass times velocity. Okay, so you'll notice it's very similar to force, because force was mass times acceleration, but now it's mass times velocity. Okay, so it's a slightly different term, but it's going to be a huge difference between velocity and acceleration. Okay, so velocity times the mass gives you your momentum. Okay, and it's this idea of a large object that's moving fast is pretty hard to stop, right? So that object has a ability to move in that direction and wants to continue moving in that direction even if other things are bumping into it. Okay, it has a lot of momentum. Okay, so large objects moving really fast have lots of momentum to them. Okay, which is why they're usually associated with things like football, right, and tackles. Okay, large objects hitting into each other. Okay, that's momentum. Okay, so let's just try a practice problem. It's a pretty simple calculation, but let's just make sure we got this down. Okay, so a cannonball is moving at a velocity of 25 meters per second and has a mass of 4 kilograms. What is the momentum of the cannonball? Okay, so let's identify what we know. Okay, so right here, we're told that the velocity is equal to 25 meters per second. Okay. And we're also told that the mass is 4 kilograms. Okay. So we know both those quantities. So now we just plug them into our equation. Okay, so momentum equals mass times velocity. Okay. So that's going to be equal to 25 times 4, 4 times 25, same thing. Okay, and that's going to give us 100. Okay, but really quickly, let's think about what our units are. Okay, so we have a meter per second here and a kilogram there. Okay, so our units are going to be kilograms times meters over seconds. Okay, so kilograms meter per second. So I write this down that the kilogram times the meters per second is always the units of momentum. Okay, sometimes you'll see it written as a Newton times a second. Okay, that's also a way you can write it. Okay, it's less common, but a Newton second is a acceptable form of momentum. Okay, because a Newton is a kilogram meter per second squared, so a Newton times a second is a kilogram meter per second. Okay, so either way, usually you'll see this one on the left, but you'll also sometimes see a Newton times a second. Okay, so but for this class, I will always write it like this. Okay, so that's the units of momentum, kilograms times meter per second. Okay, There you go. Pretty simple calculation. You're just timing the momentum, or mass times the velocity, to get the momentum. Okay? All right. So let's try this example right here. Okay? So go ahead and try it on your own really quick. So a soccer ball is moving at a velocity of 10 meters per second and it has a mass of 430 grams. What is the momentum of the soccer ball? Okay? So go ahead and try this one on your own. Okay? It shouldn't take you too long if you think through it. The main thing that you need to do is you got to be able to convert this into kilograms before you start. Okay? So if you remember, we'll use our little conversion table, so 430 grams. Okay, we'll times that by the fact that 1 kilogram equals 1,000 grams. So basically 430 divided by 1,000, that's going to give us 0.43 kilograms. Okay, so that's our mass. The velocity is 10 meters per second. So 0.43 times 10 is going to give us 4.3 kilograms meters per second. Okay, and there you go. That's the momentum of the soccer ball. Okay. All right, so pretty simple calculation, right? We're going to look at more of the impact of this later on, okay, in some of the other lessons. But right now we just want to talk about why we're looking at force and why we're looking at momentum and how it relates to things like force and these other factors. Okay. And so a lot of students get confused because we just learned how to do all these other calculations about force. So like, where does it come into play? We're talking about momentum, which is great, but we kind of just ignore force. Do we still have to calculate force, or do we just calculate momentum, or is it hidden in the calculation? Where does it come into play? Okay. And so this is a big idea in physics, okay? And this is the idea, okay? Basically, there's 3 separate quantities we can calculate in physics, but all of them are correct, but we only have to use one. Okay, so for example, we spent last unit focusing on force a whole lot, okay, which was the equation F equals ma and all the different forms of that, and Newton's laws and all that, okay, had the units of newtons, okay, and any problem we describe in physics could theoretically be done in terms of force, okay, but we usually don't want to do some problems in terms of force. Okay, for example, think about like a roller coaster, for example. If you really want to trace the motion of someone going on a roller coaster, you could, and think about the force at every single point along the roller coaster. Okay, they're going down the track. What's the normal force at that point? They're going the loop. What's the normal force at that point? Okay, the gravitational force, and you could, make this really nasty equation describing the direction of the force throughout the entire roller coaster. Okay. But it's really ugly to work with. Okay, so we don't do those types of problems with force. We're going to do those problems with energy when we get to energy. Okay, same with like a collision example, right? Momentum's really good for things that are colliding together. Okay, we could think about those things in terms of force, but then again, that's going to be really hard because the force is changing at every given moment. So we'd have to find a time-dependent equation to describe how the force is changing over time and integrate that, which is a calculus-based equation. Okay, it gets really ugly really, really fast. Okay, so the point is, when we're doing force problems, they usually have a common characteristic to them. Okay, they're usually what we call statics problems. Okay, they're systems that are not changing over time. There's a constant force, or it's in equilibrium, or something like that. Okay, those types of problems we're most usually going to do with force. Okay, we could do them in terms of momentum. We could do them in terms of energy. But it makes the most sense to do those problems in terms of force. And if we think about it in terms of force, we don't have to think about the momentum and the energy. Okay. Likewise, we're learning about momentum right now. Okay. Momentum is the mass times the velocity. It's in terms of these units. And again, it's most commonly going to be used when we're talking about collisions. Okay. Something that is interacting, things that are hitting into each other, impacts, tackles, those types of things. Okay. Those are when momentum problems make the most sense. Okay. Because we can think about things in terms of momentum. It makes it really easy to figure out the final velocities of the objects, and it makes it, again, very simple to work with. Okay. Again, we could think about it in terms of force when we're doing collisions, but it gets really ugly. Okay. It becomes a calculus-based problem. We don't want to do that right now. Okay. So if you're doing a momentum problem, you don't have to worry about the force. Okay. Most of the time. Okay, you can kind of just separate out. I'm doing a momentum problem, so I'm going to be using the momentum equations. Or I'm doing a force problem, so I'm doing the force equations. Next unit, we'll get into energy. And when you do those problems, you just think about the energy. You don't have to think about the force. Okay, so just keep this in mind. These are all different, sets of tools that we can use to solve physics problems. Certain physics problems are going to be easier to solve with a certain tool set than it is going to be with another. For example, you wouldn't use a saw to hit in a nail, right? You're going to use a hammer. It makes more sense, right? That's the tool you use to hit a nail into a piece of wood, okay? Same thing. You're going to use the momentum to solve collision-based problems. You're going to use force to solve statics-based problems. And you're going to use energy to solve dynamic-based problems, okay? So just keep that in mind. Don't think that you have to do all of them at the same time. You select one that makes the most sense and you do the problem in terms of that tool set, okay? All right, so next time we'll look more at collisions and how we can use momentum to apply that, but just keep that in mind. We have these three different sets. We're focusing on the momentum one right now, okay? So again, key idea, any physical quantity can be used to describe a physics problem. However, it is usually easier to describe a specific problem with a certain type, okay, or a certain type of physical quantity, okay? And again, example, for this unit, car collisions are usually most easily described in terms of momentum, even though you could think of it in terms of force or energy, okay? So select the tool set, use the right one, okay? Alrighty, so one thing we can think about right now to give us some more intuition about momentum is, let's think about this scenario, okay? Let's say you're going sledding, okay? It's starting to snow outside a lot in Utah, and so some of you may even been sledding, and so just think about this situation that you probably have seen intuitively, okay? Think about a little girl, going on a sled that weighs, like 30 pounds or 40 pounds. Okay, and then think about, a full-grown adult going on a sled down the same hill. Who's going to travel farther and why? Okay, so think about it for a second. Okay, maybe discuss it with the person next to you for a second. Okay, even if you don't have any background in momentum, just think about your experience. Who's usually going to travel further? Okay, and if you think about it long enough, you'll probably remember that a full-grown adult is going to travel much farther than a little kid. Okay, and the reason why is their momentum. Okay, so we know because of gravity, okay, they're going to accelerate at the same rate down the hill, so the velocities are going to be the same. Okay, so if the momentum is the mass times the velocity, and they both have the same velocities, okay, this person has a much bigger mass than this person does. Okay, so they are going to have a much larger momentum than the little kid. Okay, that means they're going to be harder to stop. Okay, and so in this example we can think about, well, it's harder to stop this person, right? They have more momentum. That means they're going to travel farther before they slow down. Okay, so again, there's lots of intuitive scenarios that you probably are familiar with momentum. Okay, but just keep that in mind. Next time we'll start doing some more inquiries with momentum. And the time after that, we'll start looking at collisions and how we can use momentum to solve those types of problems. Okay? Well, all right, I'm excited to get into momentum, but that's all we want to cover for today. Let me know if you have any questions, and thank you for watching.